Hello everyone, we are Team Data Delvers from BTech ICT second sem, and this is a short video of a quick demonstration of our capstone project. Our question is P3 Enter Queue Manager. We need to build an Enter Queue Manager for a stadium. The stadium has n entry gates and a capacity of n people. Initially, n by 2 people are randomly assigned in all the queues. Each queue is at a gate. We have to suggest the people standing in the line the time for the last person in any queue to enter from the gate and the particular queue number and in which person should switch to get a quicker entry. And also for the person standing outside all the queues, we have to suggest them that in which queue they should enter for a quicker entry into the stadium. So we have taken a few assumptions such as for the people entering outside, it takes 0 minutes to enter in a queue. The time for switch from one gate to another gate is constant and user-defined, but it has a constraint that it should be less than p. Only person in a queue which is at the last in that queue can switch for individual switching, and only one person can enter to the queue at a time from outside for entering option. The overall time complexity is bigger of n squared plus n, since m is number of people and is gate, so it might be possible that n square is less than n. That's why we have kept the time complexity big of n square plus n. We have used array and vector for making the code. Since our array has size n, which is the number of gates, and for worst case, the vector will have size n minus 1, so our overall space complexity is big of n. We are using array and vector because we are treating every person in the queue equally. So using array and vector will decrease our space and time complexity. Because if we use queue or deck, then each gate has queues. So there will be n queues and people will enter in all the queues. So for the case when all the people are entering the queue, the time complexity and space complexity will increase. The space complexity will go to m or it can go to n depending on which one is greater. But in most of the general cases, m will be higher. In that case, our space complexity will go to very high. Now let's take a run of our code. Let's take a general case where our code should fail if n, m or p anything is less than 0. So let's take number of gates less than 0. As the number of gates is negative, so the code terminated saying that the inputs are invalid. So in this case, code worked perfectly. Now let's check if for any one of the number of people or time the code fails or not. Since the code fails one again, so it worked perfectly with this error that number of gates, number of people, and the time to enter should always be positive. Now let us take one more case. If the time to enter for a single person is 0, this is also an invalid input because if the time for a single person to enter is 0, then there is no need of a stadium queue manager because everyone will enter the queue since the time is 0. So now let's test some other cases. So let's test case where the number of gates are more than the capacity of the stadium. So let's take 7 gates and 5 people. Let's keep the entering time 2 and the switching time 1.3. So let's enter 2 for giving self value to all the cues. Since the people are 5, so m by 2 would be 2 for integer. So only 2 people got assigned in the queues. Let's test this for switching from a queue. Let's choose a gate where the number of people are 0. In that case, the code shouldn't give output because since the people is 0, so no one can switch. So let's choose gate number 2. Yes, hence it shows that the queue is empty, so we cannot switch. So now let's test if the code works. If we give the value greater than the number of gates, such as 9, yes, since it was an invalid gate number, so we got a retry. So now let's give a valid value. Since there is some switching time, therefore, if a person switch and then it takes 3 minutes, so it will be more. And that's why the current place where the person was best. So now let's choose how where a person should enter. So we have multiple options. So let's choose option which is not present in the option provided to us, such as let us choose 1. Yes, since it was not a valid input because 1 was not an option for us, so we got a retry. So now let's choose a valid option 2. Now let's make everyone enter the queue. Since now all the 5% have entered, so now no one should enter to any queue. Yes, as it came that there was no people outside, so we can now not choose to enter. So now let's get the last person time in a given queue. Let's get it for gate number 7 where there is no people. Yes, since our entry time was 2 minutes, so it came that the gate has no people in the queue, so it will take 2 minutes if a person enters this queue. So now let's minimize our overall code. Since it was already minimized, so it came the same. So now let's test for some other inputs where the number of people are greater than the number of gates. So let's take 13 gates, 23,717 people. Let's give P to 3 and the entry time to switch from line is 3.24. Let's enter 1 for randomly assigning all the values. So this is the distribution of people randomly in all the gates. So now let us enter 1 to switch from a queue. So now let us switch from queue number 3. Since gate number 2 has the least people, so entering there would be a beneficial thing. So it switched from gate number 3 to gate number 2. Now let's one again choose to switch from gate number 6. Since gate number 2 was one again a preferable option, so it switched. And since the switching time was there, so when 2 times the person switched, it spent the time more than the entering time. So one people from each gate enter, and the new distribution is shown. Now let's choose that where a person should enter. So it came that you can enter to the gate number 2, and by that way a person has been entered. So now let's get time for a last person in any given queue. Now let's choose a queue which is not present, such as queue number 16. Since there was no gate number 16 in the stadium, so we have to retry. So now let's choose gate number second. So in gate number second, it will take 3667.41 minutes for the last person in that queue to enter. So now with this, let's terminate the program by entering 0. Now let's check this same program for minimizing. Now let's minimize it for the total M people. As you can see, it suggested that where how many people should enter to which gate number. And after that, what should be the switching? Since no switching was needed, so it distributed. And after all this arrangement, it will take 7,774.5 minutes to take all the people into the stadium. And after all the process, the distribution in each of the gates will be as shown. So this is how our code works. Thank you.